Hello everyone, my name is Shenyi Xu, and today I will talk you through through the project on horses disease stage classification. This work highlights the power of machine learning in addressing critical healthcare challenges. Specifically, I will discuss the pre-processing steps, the modeling process, and the analysis of results, while aligning my explanations with our module one learning objectives. The first one is the data preprocessing, clarity of explanation, and use of evidence. Let's start with preprocessing, which was pivotal in preparing the dataset for effective modeling. The dataset contains 418 samples with 19 features, including both numerical and categorical variables. It represented patient clinical data, such as bilirubin and albumin levels, which are known to indicate liver function. Missing data. So several columns such as drug and hepatomegaly had missing values. Missing numerical data was inputted with a mean, while categorical data used a mode. This ensured no data was lost, maximizing the sample size. For the target encoding part, the target variable stage originally had four levels. To simplify the classification task, we encode it into a binary target. Stage 4 positive was assigned 1, while the rest was assigned 0. This approach aligned with the project's goals of identifying several cases of horses. Imbalance correlation. The data was imbalanced with significantly fewer positive cases. To address this, I applied smooth synthetic minority oversampling technique, which generated synthetic samples for the minority class. This improved the model's ability to generalize and reduce bias towards the majority class. Feature scaling and transformation. It applies zero normalization to standardize the numerical variables, ensuring equal weight across features. Additionally, I address skewed features using log algorithm transformations, which improve the symmetry of distributions and reduce sensitivity to outliers. So for the key insights, the pre-processing ensures that the data was clean, balanced, and appropriately scared, which lies the foundation for effective model training. So for the second part is modeling, technique deeps and alignment with learning objectives. With the data ready, I turn to modeling, PyCARET, PyCART. A low-code machine learning library was used to streamline the process. This library enabled me to efficiently compare multiple models using cross-validation. The validation models, it use a five-fold cross-validation to evaluate all models. This method split the data into five subsets, training on four and validating on the fifth, rotating the folds. This approach ensured robustness by mitigating the impact of data splits, reducing overfitting and providing an unbiased performance estimate. The second is a bias variance trade-off. Among the models, tree-based methods like random forest and extra trees strike a good balance between bias and variance. These models are insensible techniques, combining multiple decision trees to reduce high variance while maintaining low bias. In construct, logistic regression, which assumes linear separability, exhibited slightly higher bias, limiting its ability to capture complex relationships in the data. So for the model evaluation, the extra tree classifier emerged as the best performing model with 75.7% accuracy validated across folds, precision of 66.29%, minimizing false positives, a balanced F1 score of 62.17%, reflecting effective handling of imbalanced classes. Logistic regression achieved comparable results with an accuracy of 73.65% and an AUC of 0.7666, demonstrating its strength in simpler datasets. For the tree-based models like extra trees and random forests were ideal for this dataset because they handle mixed data types, numerical and categorical, without extensive preprocessing. They are robust to outliers and missing values. Feature importance is inherently provided, offering insights into which clinical indicators matter most. So for the insights from results, use evidence alignment with learning objectives, patterns in the data. Features like bilirubin levels, saline levels, and age show strong correlations with the disease age stage as visualized in the heat map. This aligns with clinical expectations, validating the model's insights and the dataset's relevance. The real-world implications is a model with 75 accuracy could be integrated into clinical workflows to assist in early detections of several clinical hosts, enabling timely interventions. Moreover, the model could help healthcare providers priority like high-risk patients, optimizing results allocation in hospitals. For the part of performance trade-offs, while extra tree excellent in accuracy and robustness, its complexity increased computational requirements. Logistic regression, like its being simpler, is interpretable and computationally efficient, making it suitable for backward scenarios requiring rapid decision making with limited resources. So for the conclusion, to summarize, this project highlights the importance of robust data preprocessing, appropriate validation methods, and informed model selection in solving real-world problems. By addressing the bias-variance trade-off, evaluating tree-based models, and leveraging cross-validation, the workflow ensures reliable results. In real-world applications, models like extra trees and logistic regression can empower clinics with data-driven tools for early diagnosis and treatment priority, ultimately improve patient outcomes.